Kia ora everyone. Thanks for coming out today and listening to our research presentation on our project of finding the fire property of Eucalyptus bosistoana. New Zealand forestry relies heavily on radiata pine, as it's a staple material in construction and other building applications. Due to the nature of the timber, radiata pine needs to be chemically treated before it's used in construction, which causes environmental issues. Some examples of this are the disposal of treated timber once it's finished its use and the chemicals leaching into the soil. Therefore, we started looking into the use of hardwoods as an alternative, as they're more naturally durable and don't require treatment. That's where the Eucalyptus bosistoana comes in. It grows rapidly in New Zealand conditions and can be an alternative option in construction to using treated pine.
Eucalyptus bosistoana is classified as a Class 1 for ground durability according to the Australian standard AS 5604, which means it is exceptionally durable for outdoor use. It has a long lifespan as a timber product, with underground use lasting over 25 years and above ground use lasting over 40 years. It's also environmentally significant as it doesn't require chemical treatment, making it a more sustainable alternative compared with the more commonly used treated pine. When comparing the two species in terms of their structural properties, Eucalyptus bosistoana has higher hardness and density with values of 13 kilonewtons and 1100 kilograms per meters cubed, respectively. Radiata pine was found to only have a hardness of just 5 kilonewtons and a density of 500 kilograms per meters cubed in comparison. The increased hardness and density allow for greater dimensional stability, which is ideal for construction applications. Additionally, Eucalyptus bosistoana has superior mechanical properties, including a much higher modulus of rupture, modulus of elasticity, and parallel compression strength than radiata pine. Eucalyptus bosistoana shows up to 70% higher bending strength than radiata pine, making it a stronger and more durable choice for structural applications. Although it's found that Eucalyptus bosistoana showcase superior structural properties over radiata pine, a significant gap in the research is that there were no data on how it behaves in terms of fire performance.
There are two main fire properties that we focused on in the study, which were the heat release rate and the ignition. Heat release rate is the amount of heat energy released per unit time during a fire or combustion process, and is typically measured in kilowatts. Essentially, it shows how quickly energy is being released as heat. Time to ignition is the time it takes for a material to reach the moment where it first starts to burn and can continue burning on its own. These two properties are valuable because they help predict how dangerous a fire can get and help determine evacuation times through modelling. Both are important for building design. The bushfire attack level is a system in Australia, which classifies the construction requirements based on the risk of bushfires in the area. There are 6 bushfire attack level zones, and they're categorised based on risk factors such as proximity to surrounding vegetation, type of vegetation, and effective slope. The BAL 29 level represents the highest available level of bushfire risk for untreated timber. Therefore, our testing was designed around this criteria. The BAL 29 can be tested using a cone calorimeter with a radiant heat flux of 25 kilowatts per square metre. Testing follows the procedure outlined in the Australian and New Zealand standard 3837, and by the conclusion of the test, 2 conditions must be met. The first is that the peak heat release rate per unit area mustn't exceed 100 kilowatts per square metre, and the second is that the average heat release rate per unit area mustn't exceed 60 kilowatts per square metre. If we were able to show that New Zealand grown Eucalyptus bosistoana is compliant with the BAL 29 criteria, it could be marketed as an ideal product for use in structures such as decking or stairs in place of treated radiata. During the research process, we identified the following objectives for our project. The first objective is to use a cone calorimeter test to evaluate the fire performance of the Eucalyptus bosistoana in fire safety design, focusing on the peak and total heat release rates and time to ignition. Our second objective was to identify whether the density of the wood correlated to the experimental heat release rate, as this is one of the most important metrics in fire design. We tested 3 different species of eucalyptus across a range of densities so that we could establish a relationship between the peak heat release rate and the density of the timber. We also looked at Eucalyptus bosistoana as a possible export product to Australia and whether it met the test criteria for the BAL 29. Compliance with this bushfire standard would allow for bosistoana products to be used as a more environmentally sustainable option to radiata. Our final objective was to use the fire performance data to provide some initial values that are indicative of the fire behaviour of the Eucalyptus bosistoana.
We tested 3 eucalyptus species, bosistoana, gleboidea, and nitens. These species were chosen for their different density properties. Samples were prepared in accordance with both the ISO 5660 and AS/NZS 3837 standards to ensure consistency. Looking at the density comparison, Eucalyptus nitens had the lowest average density of 538 kilograms per cubic meter. Eucalyptus gleboidea was the midpoint with an average density at 732 kilograms per cubic meter, and Eucalyptus bosistoana exhibited the highest density at 1,125 kilograms per cubic meter. This represents a 50% higher density in Eucalyptus bosistoana compared to Eucalyptus nitens. Within each species, the 3 samples required in the standard showed relative consistency in terms of density measurements, which gives us confidence in these findings. Overall, these density differences help explain variations in fire behavior between species. Originally, our plan was to test 6 species of eucalypts so that there would be a larger range of densities to get a larger spread for correlation. However, due to constraints on budget and time, we had to reduce that.
In the study, the experimental methodology used for testing was oxygen consumption cone calorimetry. Try saying that 5 times quickly. Our first test followed the procedure outlined in the ISO 5660 standard. This ensured reliable and standardized results. For the ISO standard, the sample thickness was 10 millimeters and tested at a heat flux of 50 kilowatts per square meter. The time was recorded once the sample caught fire and sustained its flaming. The cone calorimeter recorded the gases coming from the burning sample, and the gas data was then used to calculate the heat release rate. The main focus of data was to calculate the heat release rate and ignition time. This comprehensive approach helps us provide insights to the material's behavior under fire exposure through time.
So these images were from tests conducted for this research project. The image on the left shows the apparatus used alongside a sample undergoing testing. The image in the middle is right after the test finishes, and the image on the right shows sample after the testing.
From the heat release rate results, when testing 10 millimeter thick samples, we found that the Eucalyptus bosistoana stood out with the highest peak heat release rate at 257 kilowatts per square meter, and the highest total heat release rate of 106 megajoules per square meter. When comparing species, the Eucalyptus gleboidea recorded a lower peak at 224, and the nitens had the lowest at 201 kilowatts. All species followed a similar heat release rate curve shape, with early initial peaks and a second peak further along in the test, but the bosistoana maintained higher values throughout the testing. The heat release rate analysis shows that higher density correlates with higher peak heat release rate, and bosistoana's peak was delayed, occurring at about 550 seconds to 600 seconds after the test, likely reflecting its denser structure and slower burn progression.
We used the measured density of our samples across the different species to compare with their respective peak heat release rate. We then analyzed the data using linear regression to determine the degree that the density and heat release rate correlated with each other. We tested the density against both the peak heat release rate and the total heat released, and found that both measurements showed a strong positive correlation. The R-squared value for peak heat release rate and density was 0.8785, and the R-squared value for total heat release versus density was 0.8653. As these values are close to 1, this suggests a strong positive correlation. However, this correlation was achieved with a relatively small sample size. The future research with more species and samples will be recommended to evaluate this correlation further. We also ran a one-way analysis of variance to see if the results we obtained from the data were statistically significant. This gave us a p-value, and for the correlation to be statistically significant, this p-value needed to be less than 0.05. Our one was 1.16 times 10 to the negative 6. We also obtained an F statistics from a NOVA test, which measures how much the group mean differs relative to the variation within the groups. The test gave us values for the F statistics and an F critical value, which we could then compare with each other. For our test, our F statistic was 282.1, which was larger than our F critical value, which was 5.14. This means we can conclude that the results our correlation are statistically significant.
A thief experiment involved an indicative BAL29 compliance test. Under BAL29 bushfire standard requirements, the materials must withstand a 25 kilowatt heat flux for 20 minutes with compliance criteria of peak heat release rate being less than 100 and the average being less than 60 kilowatts per meter squared. To satisfy this criteria, the cone calorimeter test is run with different parameters. A 20 millimeter thick sample was used instead of the 10 millimeter from previous tests, and the imposed heat flux is lowered from 50 down to 25 kilowatts per meter squared, which simulates a non-piloted ignition scenario. We found that the average heat release rate was 30.6 kilowatts per meter squared, which is well below the 60 kilowatt requirement. However, the peak heat release rate reached 132.7 kilowatts per meter squared, which exceeds the 100 limit. As a result, our test sample didn't meet the BAL29 classification criteria. This mixed outcome is important. While average heat release rate performance is promising, further reduction of peak heat release rate is required. Future research could explore densification or surface modifications to optimize fire performance and enable full BAL29 compliance for Eucalyptus bosistoana.
Eucalyptus bosistoana demonstrated significantly longer ignition times, ranging between 52 and 64 seconds compared to the other two species. This reflects a greater resistance to ignition under an elevated heat flux, which is a key performance indicator for fire resistance materials. Eucalyptus gleboidea showed ignition times between 29 and 37 seconds, while Nitens had the shortest times between 14 and 19 seconds. Within each species, ignition times were highly consistent with minimal variation between samples. This consistency indicates reliable material behavior under the repeated testing required by the standard. From a fire safety perspective, longer ignition times are advantageous as they delay the onset of flaming ignition, giving more time for detection and potential intervention. These differences are influenced by wood density and thermal inertia. Denser species like Eucalyptus bosistoana require more energy to reach ignition temperatures, which slows down the heating and pyrolysis processes.
So, our study aimed to investigate the fire properties, providing data for its potential use as a construction material, and this allowed us to draw our testing allowed us to draw several conclusions. We found that density correlates strongly to both peak and total heat release rate, with R-squared values at 0.87 and 0.86 for each, which shows that density can be used as an indicator for fire intensity. Our pilot test to determine if bosistoana was BAL29 compliant found that while the average heat release rate was well under the required level, the peak heat release rate was almost double the allowable level, which suggests that it doesn't meet the requirements for bushfire-resistant timber. However, repeat experiments with a greater sample size would be fully required to fully determine this. During our journey, we identified several limitations to our work. Unfortunately, due to a broken calorimeter here at UC, we tested our samples privately through brands. This created a constraint to both cost and testing time, so we had to sacrifice some of our extra test samples from our original plan. This meant that we had a lot less samples and species to work with, which could have affected the accuracy of our results. And therefore, an opportunity for future research is to repeat our study with a much larger sample size and range of species, as this can further account for the natural variability in timber to get more accurate results. Other possible avenues for future research include testing the fire properties at a range of different heat fluxes or evaluating how bosistoana performs as a biofuel, as our study established that this timber exhibits high heat release rates and density. Thank you very much for the plan.
Thank you.